Hi class, I hope you're all doing well. So welcome back for another week. This week we're going to start looking at the actual exoplanets that we've discovered elsewhere in the galaxy. At this point in time, we've discovered some almost 5,000 individual exoplanets, and there are about 3,000 more that we think are there, but they have yet to be confirmed by follow-up observations. We find ourselves in an age where we are literally drowning in exoplanets. The number that we know is enormous, which has a lot of scientific potential because it means we have lots of examples to try and understand planets. We have lots of examples to think about where we might look for life elsewhere in the universe, but it's also very difficult because there's so much data to work with that we just have so many different things to try and piece together to try and understand the story. So it's a very exciting time to be working in exoplanets in particular, but in astrobiology and astronomy largely because of this. So in my background here today, this is a piece of a map. You can't see the whole thing because it stretches off the edge. So this is the entire sky. Okay, so across the top here, you see some numbers. That's called right ascension. So that you can imagine lines going up and down the map like this. That's kind of like longitude on the sky. Okay, and then horizontal lines going across this map would be like latitude on the sky. And each one of these colored dots is a star around which we have discovered an exoplanet. The coloration is indicative of the different methods by which we've discovered the exoplanets. We'll talk about those next lecture. And so you'll notice that we've discovered them all over the sky, which means we've discovered them everywhere in the Milky Way galaxy that we've looked. You'll see some very big clusters like this one right here. Okay, so that is an area of the sky where the Kepler mission was looking for exoplanets, and we'll talk about them next lecture as well. But far and away, tons and tons of the exoplanets that we know of come from that field over there where Kepler was looking. Okay, so let me go ahead and start a few slides. So what we're going to talk about today is really the challenges we face in looking for exoplanets, okay? So I want to talk about the kinds of things that we struggle with, the kinds of things we have to face up against, and then we will use that to describe the missions and the discoveries of the exoplanets that we've actually found. Okay, so in the background here, this is arguably one of the most famous observatories in the world. This is the Palomar Observatory outside of Los Angeles, kind of between Los Angeles and San Diego, with the Milky Way in the background. Up until the 1990s, I think, the Hale telescope at Mount Palomar, the 5-meter telescope, was the largest telescope in the world. Today, we still use Palomar for all kinds of follow-up and spectroscopic surveys of all different kinds of astronomy. But it's a very nice picture because it shows the Milky Way, which is why I put it up here. So we're going to talk about some of the challenges here. So in this half of the lecture, we're going to talk about basically resolution challenges, how big things are and how hard it is for our telescopes to see things that are very far away and very tiny. Okay, so we'll talk about angular size, how big something appears on the sky. We'll talk about angular separation, the ability of a telescope to separate or distinguish two objects that are very close together on the sky. And then we'll talk about the brightness of the stars, which is the other big problem we face. Okay? So when you look at the stars to look for planets, you're really faced with this singular fact. The stars are the things that are easy to see in the telescope, and the planets are not, because the stars are enormously bright compared to the planets that we're looking for. If you just look in our own solar system and you compare the brightness of Venus to the brightness of the sun is 630 million times brighter than Venus is. Okay, so those of you who have seen Venus, you can see it right now in the evening sky. In the west, right after the sun goes down. This image here is Venus in the evening sky. Venus is very bright to your eye. You can see it. It's enormously easy to see compared to everything else in the sky. But you have to wait for the sun to go down. Even when the sun's up, Venus is still right there, and you can actually still see it with your naked eye if you know where to look. But the brightness of the sun overwhelms us, okay? And so this is exactly the same problem that we have when we are looking for planets around other stars, is that the brightness of the stars overwhelms us. And so we have to somehow come to grips with that and deal with the fact that the stars are easy to see, but what we're really interested in is the planets, okay? So there's two things we can do. We can look for the planets directly, okay? That's hard for the reasons that we just said. Or we can look at the planet affecting the star, okay? And both of those techniques are viable. Both of those techniques work. Okay, so we're going to talk about both of these in the course of the two halves of lecture today. Okay, so let's ignore brightness for a moment and let's just talk about the ability to see two objects. Okay, and so for this example here, we're imagining two objects of the same brightness. Okay, so they're just very close together, not necessarily a planet and a star where they're still very close together, but one is enormously bright. Okay, so the ability to separate two objects, to distinguish that there's clearly one object here and one object here, is called angular resolution. Okay, and over here on the right, these are images of two stars, roughly equally brightness, right next to each other. And at the top, we have the view through a small telescope, that is to say a small diameter telescope, or a telescope at very low magnification. And what you can see is one bright spot. Okay, you can't really see two distinct stars. As you increase the magnification, going down the images here, or as you increase the diameter of your telescope, you see that the two stars start to elongate into something that looks like a peanut shape. But there's still not really two distinct stars there. There's some hint that there is. You see that kind of peanut-shaped thing there, but there's no dark space between them. So you can't really tell, are there really two stars there, or is it just a funny shaped star shaped like a peanut? Okay, well, if you keep increasing the magnification or you keep increasing the diameter of the telescope, finally you get to the point where you see two stars very distinctly right next to each other. Okay, now you may not have encountered this before, but you will be familiar with this if you've ever spent some time looking through binoculars. If you have a pair of binoculars that you use to look at birds or something like that, and you're looking at things that are really far away, you may look, you know, at the park down the street from your apartment, and with your naked eye, you just see trees. But through the binoculars, when you increase the magnification, suddenly it makes it very distinctly clear that there's two trees right next to each other, okay? And so that is what angular resolution is about. Magnification helps take things and spread them apart, but it also matters on the diameter of the telescope, okay? So we can quantify this. We can actually do calculations. Someone can ask you, could this telescope see this? Could you see a crater this big on the moon using the Hubble Space Telescope? You can answer questions like that. All you need to know are the diameter of the telescope, d, and the wavelength of light, lambda, that you're going to look at, okay? So if you do that, then you can write down the angular resolution of the telescope. If you talk to your friends who are physicists, they'll call this the Rayleigh criteria. Okay, you don't necessarily need to know that unless you have to look it up on Wikipedia. Okay, but the angle, the angular separation, and I'll draw you a picture of this to show you what I mean by angular separation in a minute. Okay, the angle theta between the two objects that you're looking at is given by this formula, 1.22, that's just a number. You take the wavelength of light that you're using. So for a telescope you and I might use in our backyard, the wavelength is some visible wavelength of light. So right in the middle of the visible spectrum is green light at about 500 nanometers, 5 times 10 to the minus 7 meters. And then you divide that by the diameter of your telescope. Okay, so the size of the lens on the front of your telescope or the size of the mirror that your telescope's using to gather light. You divide those two numbers, you multiply by 1.22, and that gives you the angular separation in these funny angle units that we use called radians. And some of you may remember from when you took geometry that radians are one number set that we use to describe the sizes of angles. If you do want to use more familiar degrees, which are the things that are marked off on a protractor when you read angles, then the formula looks very similar. There's just this conversion factor, 180 degrees over pi, that converts this angle theta into degrees when you measure it this way, okay? Now, if you use these formulas, you absolutely have to be careful that d, the diameter of your telescope, and lambda, your wavelength, are measured in the same units. That means if you express d, the diameter of your telescope, in meters, then lambda also has to be expressed in meters. If you were to express d in inches, then lambda would have to be in inches. If you expressed lambda in nanometers, then d would have to be expressed in nanometers. So you just want to make sure those units are the same size, and then you can use these formulas with impunity. Okay, and I comment there, I almost always convert everything into meters. As we discussed early on in the class, SI system is the one that is most comfortable for most scientists. It's the kind of standardized system of units that we use in physics and astronomy in particular. Okay? So this angle, angular resolution, this angle theta, this is what it means. So there you see up in the sky a red star and a blue star. Those are two stars that are real close to each other in the sky. And when we say what is the angular separation between them, I mean if I draw a line from one star down to my telescope and then back up to the other telescope, like two sides of a triangle, then the angular separation between those two stars is the angle between those two lines as shown in this diagram here. Okay, now it doesn't have to be two stars. As I said right when we started this, you can talk about can your telescope resolve all kinds of things using this angular resolution formula. So if you want to talk about can I see features on a planet and tell the difference between the size of a crater on a planet or the diameter of a planet in my telescope, you use the exact same formula. You just draw those lines to the things that you're trying to measure the angular separation between. Okay? Now this is only part of it, right? This is basically telling you what is your telescope capable of doing. Okay, but oftentimes you want to build a telescope. This is the case for exoplanets. We want to build a telescope that's capable of being able to do certain things. So we have to know not what can the telescope measure in terms of the angle theta. We need to know what angle theta does nature actually tell us we need to measure, okay? And so that is what we call angular size. So if you were to imagine your star and your planet, your star and your exoplanet, or the diameter of some planet where you wanted to measure surface details across the planet, you can imagine drawing a big triangle from Earth out to the planet, across the planet and back down, or you can measure from Earth out to the star, over to the exoplanet and back down, just like these triangles here. Okay, and so if you know the true separation, that is the distance across the planet or the separation between two stars or between a star and an exoplanet, and you know how far away it is, then that triangle that I've drawn there in those pictures completely defines that angle theta that's marked again. And so we have a slightly different formula. This is the angular size formula, which you may have encountered before from when you took geometry. Okay, so it's written in the following way. Again, if you're measuring theta in radians, it's just a number, okay? Then the size, the separation, or the diameter of an object is given by the distance to the object times that angle theta in radians. And again, if you're more comfortable with degrees, then you can write it in this similar looking formula. There's just a conversion factor pi over 180 there to express it in degrees. Now, just as was the case with our angular resolution formula, there's a caveat here, and that is both S and R have to be measured in the same units. If you measure the distance to the distant star in light years, then the separation between the star and the planet must also be in light years. That is very inconvenient, right? How many light years away from the sun is the Earth? Well, the Earth's only 8 light minutes away from the sun. It's some fraction of a light year, but it's a very tiny number that's hard to remember. So in this case, you have to, again, be careful and convert your units to the same unit system for both the distance to the object you're looking at and the physical separation within the object that you're trying to measure. I almost always use meters again, because meters are the common unit that we use in physics and astronomy. Okay? Okay, so how do we use this? Why am I telling you these things? So like I said, this is all about designing the telescopes that we want to use to look for exoplanets, okay? So telescopes are all about the diameter, okay? So here is arguably the most famous telescope in history, the Hubble Space Telescope. The diameter of its mirror is 2.4 meters, Okay, so that's taller than you or I are if we were standing straight up. Okay. The successor to Hubble is a telescope called the James Webb Space Telescope. It was supposed to be launched this upcoming year. We will see when it actually launches with the world in the state that it is. Okay, but it is much larger than Hubble, as you can see there. The mirror on the James Webb Space Telescope is so large that it's being flown in little segments, okay, and the mirror is actually going to fold up, and they'll launch it. It'll get to where it's supposed to be in space, and then that mirror will unfold like an origami flower. Okay, it's remarkable technology. It's the first telescope of its kind to be deployed this way, but it's going to be tremendously bigger compared to Hubble. Why do you make it bigger? Well, because you can gather more light, which means you can see dimmer things, and at bigger diameters, you have better angular resolution. And this is what the game is all about in astronomy. Okay. Now, to design space telescopes takes a long time. So even though we're just about to launch JWST now, we're already thinking about and working on the designs for the telescope that's going to come after JWST. We haven't decided what it is yet. There are a couple of examples. I'll show you both of them in this lecture. But one of the ones that you may have heard about that the community is very excited about is called LUVOIR. So LUVOIR is the Large Ultraviolet Optical Infrared Telescope. And it is enormous, even compared to JWST. LUVOIR is going to be at least 12 meters across. And just like JWST, we will have to fold it up and send it into space, and then it will unfold. Okay? So let's use the specs for LUVOIR to talk about what it's going to be like to try and make an image, take a picture of an exoplanet. Okay, now what I'm doing here is I'm going to use these two formulas that you and I just talked about. This is the simplest calculation you can do to show what it will be like to image an exoplanet. It's going to be hard, as you're going to see. There are many other techniques that we use. There are advanced imaging techniques and advanced methods for which you take a telescope and can make it do a little bit better than the number you and I are talking about. But by and large, this is the number that you should be thinking about. Okay, so let's do this calculation. So how does it work? So let's start with the two formulas. So remember, one is the angular resolution theta that our telescope can measure. That's the blue box. And it depends on the diameter of the telescope d and the wavelength lambda. This other, the red box, is the angular size of an object in the sky based on the physical separation s and the distance away r. Okay, so let's write down all of the numbers that we know for a specific problem. And the specific problem I'd like to ask is, what is the smallest size feature that LUVOIR could see in an exoplanet orbiting Proxima Centauri, which is the closest star to the sun? Okay? Okay, so the first thing I'd always do is I write down all my numbers and I make sure I have them right at hand. I know what the values are. I write down their units. I convert them to the units that I like to use, which in my case is always meters. Okay, so the distance to Proxima Centauri is 4.3 light years. If you convert that to meters, it's 4.07 times 10 to the 16 meters. Telescopes like LUVOIR can see many different wavelengths, but let me just pick the wavelength that our eyes can see. So I picked that 500 nanometers, that kind of green-yellow light that our eye can see. And if you convert 500 nanometers into meters, that's 5 times 10 to the minus 7 meters. And the diameter of LUVOIR is going to be something like 12 meters. Okay, so if you look at all of these quantities I've written down and you look at our two formulas up there, you'll see we know everything in those formulas except theta and s. Okay, so the first thing I'm going to do is I'm going to compute theta using the blue box, and I'm going to take whatever value I get, what angle can LUVOIR measure, and I'm going to put it over into the red formula, which says, what's the separation correspond to what LUVOIR can measure at the distance of Proxima Centauri? Okay, so I start by calculating the angular resolution of the LUVOIR. 1.22 times the wavelength, 5 times 10 to the minus 7 meters, divided by the diameter of the telescope, 12 meters. And I get 5 times 10 to the minus 8 radians. Now, if you were comfortable converting this into, more comfortable converting this into degrees, you can certainly do that. I'm going to leave it in radians because I'm just going to put it over in this formula over here, which is also expressed in radians, okay? So if I take that theta together with the distance to Proxima Centauri, I can tell you what S is. Given that LUVOIR can measure this little angle here on Earth, if I draw that triangle, starting with that little angle, all the way to Proxima Centauri, what's the distance across the bottom of the triangle? What's the smallest thing that LUVOIR can see? Okay, so I take 4 times 10 to the 16 meters, I multiply it by 5 times 10 to the minus 8 radians, and I get 2 times 10 to the 9 meters. 2 million kilometers is the smallest thing that LUVOIR can see in the Proxima Centauri system. Okay, that's about twice the diameter of the sun. So even though Proxima Centauri is the closest astrophysical system with planets in it to the Earth, we're not going to be able to image the individual features on the surface of a planet. Okay? Okay, this is really a hard problem. So we have to either have bigger telescopes, look for bigger planets, develop better techniques, but the fundamental message here is that measuring small details on exoplanets with telescopes is hard. Okay? Now let's go back to the problem that stars are too bright. So this is absolutely fundamentally the biggest problem we have. Okay, so this picture here is not of a star and an exoplanet. This is of a star and its companion star. So this is Sirius, the brightest star in the sky, the big bright star in the middle. And right next to it, down on the lower right, you'll see a little fleck of a star. That's called Sirius B. It's sometimes called the pup. Okay, and these two stars, you can absolutely see them and image them just like in this, but it's very hard to see the pup because Sirius is so bright. If you look at the orbit of Sirius and the pup, these two stars are going around each other just like planets go around the sun. You see that the pup is in an orbit that takes about 50 years to go around. Okay, so that's something like, let's see, it must be about the orbit of Saturn is about 50 years long. You can go check that. I should have checked that before I started lecture. Okay, and the separation between them, it varies actually between 8 astronomical units and 31 astronomical units. Okay, so 8 astronomical units is something like the orbit of Jupiter or so. Okay, so this is exactly the kind of range for habitable zones that we want to look for. For most stars, for really hot stars like Sirius, they may be out in those wide separations. But for most stars, the habitable zone is going to be even closer than this 50 AU. So you can imagine that if I took the pup and pushed it even closer to Sirius, it's going to be much, much harder to see. Okay, and planets, since they're not stars, the pup is a star, planets are going to be even dimmer than this star actually is. So detecting planets directly around a bright star is going to be very difficult. Okay, but there must be a way to do it. And in fact, there is. Okay, so the way you can do it is exactly the way you do it when you're at the ballpark, right? You're at the ballpark, you're trying to see, you know, where that ball the Cubbies hit just went, okay, and the sun's in your eyes. So you hold up your hand to block out the sun, and by blocking out all that brightness, you can see smaller or dimmer objects without the glare of the sun disturbing you. Okay, and that's exactly what we can do with telescopes. So here's an image of a typical bright star, and one of the things that we're proposing you do is you build a telescope that has what's called a stellar coronagraph or a star shade. You put it in front of the star, and with the glare of the star blotted out, a dim planet will show. And if you uncover the planet again, the brightness of the star overwhelms you again, and the planet fades away. Okay, so this is one technique for seeing planets directly by blotting out the bright glare of the parent star. Now, this is a proposed mission. There is another mission in the same time frame as LUVOIR, proposed called the Habitable Exoplanet Explorer, or HABEX. In this case, they're going to have a star shade. So you see the telescope there is on the right. That's the main spacecraft. But there's an additional piece that free flies that extends a star shade that's 72 meters in diameter, but it's 124,000 kilometers away from the main telescope. So clearly in this image, it's not up to size. But the basic idea is with the star shade way out there, okay, it's 72 meters across, but it's 124,000 kilometers away, that it'll be small enough that it can block out a star, but still leave room for the planets to peek around the edge of the star shade. Okay, so this is the direct imaging kind of technology that we are thinking about. We have some examples, and I'll show you some movies of this probably next time, where we have managed to blot out the light of a star, not using this star shade technology, but using another kind of technology, and we can actually image exoplanets directly that way. Okay, so this is a little bit science fiction-y. Both of these missions are a little bit science fiction-y, but they're the next step we're heading towards beyond using the kind of telescopes that we have today in order to get much better at imaging exoplanets. Okay? Okay, so that's all I'm going to say for this half of the lecture. We'll come back next half of the lecture and we'll talk about how we can use light to tell us something about the exoplanets. Okay, so I hope you're all doing well. Take care of yourselves, and I'll talk to you later.